So in this video, we'll see covalent network solids. So in that, we look on, so what are covalent solids? Covalent solids are nothing but they are formed by network or chain of atoms or molecules held together by a covalent bond. That is basically a covalent solid. So covalent solid or covalent network solid. So basically, perfect examples are diamond and graphite. So perfect single crystal of covalent solid is known as single chain molecule. Okay, perfect a perfect single crystal of covalent solid is known as single chain molecule. So, for example, structure of diamond. It's an example for a covalent solid because they are formed by a network or a chain of atoms held together by covalent bonds. So chain of carbon atoms. Okay, so they are sp3 hybridized carbon atom bonded to four other carbon atoms of tetrahedral array to get a chain network. Okay, the carbon atom form the six membered ring. It forms a six membered ring. Like this is how a diamond looks like. So basically, diamond, you know what is the electronic configuration for carbon? It is nothing but 2, 4, and each carbon shares electron with the four. So a carbon will be having four electron, and this four electron will be shared by another carbon having say. Okay, that is what covalent bond, and they form single bonds. So it is basically a network solid. Also, the entire solid is endless repetition of carbon atoms bonded to each other by covalent bonds. The entire solid is the repetition. So see here. So this is a carbon molecule with the four electrons, and we are connecting this. These are the other electrons forming bond. And next, what happens is, okay, say here a thing will atom will combine like this, and say here another one atom will be combining like this, say another atom. So this is the covalent network. So this is actually similar to zinc zinc blend ZNS. Okay, it is the structure is actually similar to zinc blend, but the only difference is there zinc or sulfur is present at the center. So here it is not like that. Okay, so unit cell of diamond is described as a FCC array of carbon atoms with four additional carbon atoms instead of inserted into four of the tetrahedral holes. You know, carbon have tetrahedral geometry, right? So the tetrahedral holes, in tetrahedral holes, these four additional carbon atoms is inserted. Okay, so it is an FCC array of carbon atoms. So therefore, yes, except the difference in zinc blend is that they are FCC array of sulfur, but atoms in tetrahedral holes are sulfur or vice versa. Okay, that is the difference. And coming to the physical properties, it is of course it is hard, then high melting point, and this cannot be easily deformed. Okay, so instead, but we can shatter them, and they do not conduct electricity very well because why? No free electrons are there. So they are not a good conductor of electricity. Also, elemental silicon, okay, has same structure as silicon carbide. So which has alternating silicon carbon and a silicon atom. This is also an example, or we can compare like zinc blend as we did. And now melting point is also very high. So it is the hardest, one of the hardest substance which is known. Yes, diamond is one of the hardest substance that we know. Also silicon carbide, that is silicon carbide, as I said, it has also a silicon carbide, as I said, it is similar to diamond. But the thing is that there we have alternating silicon carbon atoms. Here all the atoms are carbon only. Okay. So here, what is the commercial use? It is used in the abrasive in sandpapers and grinding wheels. We use for grinding wheels. Also, this thing also, in case of silicon carbide also, they are difficult to deform or melt because of the very strong covalent or polar covalent bonds. Okay, very strong covalent bonds existing between. In case of diamond, we have between carbon carbon, and in case of silicon carbide, it is between silicon also in silicon carbide, silicon oxygen. Such polar bonds are also there. Okay. Strong covalent or polar covalent bonds. These must be break or this must be broken. So these two compounds have very high melting energy, melting point. Also, they are not easily, we can't deform them easily. Now we come to graphite. Graphite is also another example of covalent network solid. Okay. So the most stable, the most stable form of carbon is nothing but the graphite. So it consists of sheets of carbon atoms covalently bonded together, and these sheets are stacked to form this. This is the one single layer of formed by, like, they form like this. Like what? Carbon atoms actually bond each other and form covalent bonds each other to form a sheet. And these sheets are arranged like this. Distance between individual sheets is 2.5, means 2.5 is the distance between two sheets. That means actually the in a sheet carbons are so strongly covalently held. But the point is between sheet we have a negligible distance. We have an enough distance actually. It's not again. It is 2.5 times the distance between atoms within each layer. Right? Means if if two atoms space in a layer of between two carbon atoms, say if it is X, then between between these two layers in between two layers, it is around 2.5 times that X. Okay. So it has a very large structure and each layer endlessly bonded network of carbon atom. Also, there is no bonding in Z direction. It is a 2D. Okay, there is no bonding in a Z direction. That's also important. And distance between layers 2.5 times the distance between atoms within each layer. Okay. Now coming to the solubility, actually these are insoluble in water and organic solvent. Why? Because the force of attraction between individual molecules, like attraction between this carbon atoms, it's very high. That is, the covalent bond is very strong. So it is not easily it is not easily soluble in, it can't form bonds with the water molecule. So the attraction between solvent molecules and carbon atom will never be strong enough to overcome strong covalent bond. That means between carbon atoms there exists a very strong covalent bond. So the strength of that particular covalent bond will not be able to overcome the bond which will be forming when we are using a solvent and the bond formed between a solvent and the carbon. Okay, so therefore this is insoluble. Also, the significance of graphite is they conduct electricity because uh, why they conduct electricity is because delocalized electrons are present. Okay, so delocalized electrons are free. Actually, what are delocalized electrons? These electrons will be freely moving, right? So delocalized electrons are free to move throughout the sheet. So if a piece of graphite is connected into a circuit, electrons can fall off one end of the sheet and can be replaced with new ones to other end. Means the electrons are delocalized electrons are free to move. So they conduct electricity. In case of diamonds, all the four electrons are involved in bond formation. Here it is not like that. Okay. So in carbon atom, means here the each carbon atom will use three of its electrons to form single bonds and its three close neighbors, and this leaves a fourth electron in bonding level. There is a fourth electron in bonding level, and this bonding level fourth electron, this delocalized electron, which is free to move. So that what happens, it conducts electricity because this delocalized electron will be freely moving throughout the sheet, and if a graphite piece is connected to a circuit, then electrons can fall off one end of the sheet and replace the new one at the other end. Means here we have a three bonds and a fourth electron in bonding level. So these spare electron means the fourth electron in each carbon uh, becomes delocalized over the entire sheet in one layer. So there is no longer associated directly with a particular atom, but they are free to wander throughout the whole sheet. So because of this delocalized electron, since the delocalized electron are free to move everywhere within sheet. So there is each electrons are not fixed in any particular carbon atom. So, but however, there is no direct contact between these relocalized electron in one sheet and those in the other. Actually, for example, if the first layer has many delocalized electrons, say we'll say it is A, and second layer has as same as delocalized electron, say it is B. So actually, there is no direct contact between these two. Okay. Actually, there is no direct contact between the delocalized electron of one sheet and the other, but they are free to move. This can move here, this can move here. It's free to move over the entire sheet. Okay. These electrons are no longer fixed to a particular carbon atom. Okay. Atoms within sheet are held together by strong covalent bonds, stronger than diamond because of the additional bonding caused by delocalized electrons. So delocalized electron adds more significance to graphite compared to diamond. Okay. So atoms within a sheet are held together by strong covalent bonds, stronger than diamond. Also, this graphite actually have high melting point, but density is too low. You'll see the reason here. In graphite, it is an ultimate example of weak van der Waals dispersion force. What is van der Waals dispersion force? We know it is a weak force. As we said, between carbon atoms, there exists a very strong covalent interaction. Then from how can the weak van der Waals dispersion force be in graphite? So that is because in between layers, that is the inner sheets, carbon atoms are very strongly held by covalent force. But in between sheets, they have a very good distance. So there exists the weak van der Waals dispersion force. So as delocalized electron move around the sheet, very large high temporary dipoles can be set up and which will induce opposite dipole in sheet above and below. So throughout the whole graphite crystal. So okay. Significance of delocalized electrode. First significance, as I said, yeah, it is able to conduct, graphite is able to conduct electricity because of this delocalized electron. Also, it is much harder than, or we can't say it as it is much harder. This graphite is much stronger. The bonding in graphite or atoms in a sheet are held by very strong covalent interaction. So that is they are stronger. Because of that is also because of this additional bonding created due to the delocalized electron. The second point is okay. We said then the third significance of this delocalized electron is because of this freely moving delocalized electrons, temporary dipoles are induced. So in between two sheets, uh, say opposite dipoles are created in between. Like these two sheets creates opposite dipole because of this weak van der Waals force. So temporary dipole is set up, which will induce opposite dipole, which will induce opposite dipole in sheets above and below. Throughout the graphite crystal, this is the same. Also, graphite has very high melting point. In order to melt graphite, it isn't enough. Like okay, I said there is a weak van der Waals dispersion force between two sheets or two layers. We can say it like that, two layers. But even though if you are able to break that bond, very weak bond between these two layers, this is not enough to melt graphite. To melt graphite, we should break that covalent bonds at whole structure. Okay, covalent bonding should be broken throughout the crystal. Then only we can melt graphite. So that is the other point. So also we know that it is soft, slippery, feels slippery feeling, and we use it in pencil also as dry lubricant for many things like locks and all. We use graphite. Then low density of graphite. This low density of graphite is because of the relatively large spacing between this sheets, or we can say it as layers. Okay, these between these sheets, a large number of space is vacant, right? So this, because of this relatively large amount of space that exists between two sheets, graphite is having low density. Okay, otherwise it won't, right? Yes. So these are the things I needed to mention in this covalent network solids. Basically, nothing. Covalent network solids are nothing but what covalent network solids are nothing but covalent solids. They are covalent solids formed by network or chain of atoms or molecules held together by strong covalent bond. Okay, held together by covalent bond. Perfect examples are graphite and diamond, which is allotropes of course, carbon.